In this lecture, we would like to derive momentum conservation during collision using impulse momentum theorem, and then we will do a few examples in collision. So for collision, we need to distinguish forces, two different kinds of forces, internal force and external force. Internal force means if you have a system, you have a few objects within the system, then force from those objects inside the system on each other, we call it the internal force. A force exerted by object outside of the system on any object inside the system, we call it external force. So let's think about these two balls. So the picture shows two balls moving, and we are looking at those two balls up from top of the table. So we are seeing the table, two balls on the table. And what do we see? The two balls move and they will collide here. And during the collision, they are exerting a force on each other, and we call those forces from green ball to the purple ball, or the force from purple ball to green ball. Those are internal forces, because we treat these two balls as a system. A two-ball system, the force between those two balls are internal force. Now, if they are on the table, then gravity, normal force, they are from object outside of this two-ball system. We call it external force. Now let's have a look at using impulse momentum theorem to look at the motion of those three balls. So we have ball 1, M1. The momentum change of ball 1 from impulse momentum theorem should equal to the total force acting on ball 1. So this final momentum of ball 1, initial momentum of ball 1 should equal to the total net force. But we split the forces to external force on 1. This is external forces on 1. And the internal force on 1 from ball 2. So those are net force, the total net force acting on 1. And this is force from ball 1 on ball 2, external force on ball 2. So there's a total net force on ball 2 times T, which is the impulse on ball 2, gives the change of the momentum of ball 2. Now, what's happening if you add those two equations together? So we're arriving at this equation. However, we know the forces between ball 1 and ball 2. We need to use the force between ball 1 and ball 2. This is a linear action-reaction pair from Newton's third law. So F12 and F21 should equal magnitude and opposite direction from Newton's third law. So we can use it here if they are equal magnitude and opposite direction. So these two terms should sum up to 0. And this term is momentum of ball 1 and momentum of ball 2 add up together after the collision. There's a momentum of ball 1 plus momentum of ball 2 add up together before the collision. This term gives us initial momentum of the system before the collision. This term gives us final momentum of the system after the collision. The left is total external force acting on the system, acting on the two-ball system, the total impulse total external force times delta T gives you the total impulse acting in the system. So we have this relation, sum of external impulse on the system equals the change of momentum of the system. So this is impulse and momentum theorem applying to a two-body system. Now, what's happening if the sum of external force is 0, or if the impulse of external force is 0, we get external impulse is 0, so change of momentum is 0, so we have final momentum equals initial momentum. So we have principle of conservation of linear momentum. The total linear momentum of ideas as isolated system is conserved. An isolated system, which means the sum of average external force acting on the system is 0. So we can use to do one example. So you have two skaters starting from rest, then push off against each other on ice. So we treat friction to be 0 in this problem. And one is a woman, 54 kilogram, another one is man, 88 kilogram. Now we know after the push, the velocity of the woman, the speed of the woman is 2.5 meters per second. What will be the velocity of the man? So if we look at this problem, we want to use momentum conservation, principle of momentum conservation. We treat those man plus woman as a system, as a two-body system. So we do free body diagram analysis. So we have normal force on man, normal force on woman, weight on man, weight on woman, and there's no friction as it says in the problem. So normal force on man, normal force on woman. This is 1, 2, weight 2, weight 1. So Fn1 and W1 should cancel. Fn2 and W2 should cancel. So we have this man and this woman as an isolated system. External force add up to 0. So there's no external net force acting on the system. There is only internal force, which is a push from the man to the woman or from the woman to the man. Those are internal force. So momentum of the system is conserved in this case because there is no external force acting on the system of these two persons. So we have final momentum equals initial momentum. Final momentum is momentum of the woman plus momentum of the man. Initial momentum, because they start from rest at the beginning, momentum man is 0, momentum woman is 0 too. So initial momentum is 0. So we just need to solve for the velocity of the man. Vf2 equals negative m1 m2 vf1. Now m1 54 88 2.5 meters per second, the final velocity of the woman. So the velocity of the man should be actually 1.5 meters per second. And it's negative. After solving it, we automatically find it's negative because you see, if you choose this to be a positive, the woman is moving in positive direction, the man is moving in negative direction, negative 1.5 meters per second. Okay. Now the classic bonestic pendulum problem. So you have a bullet struck into the block, and after the bullet is embedded into the block, they will swing up together to a height. So once you're using the information, we know the mass of the block, the mass of the bullet, we know how high the block is going to swing up. We want to find out what's the initial velocity of the bullet. So there are two processes. First, the bullet struck with the block. This is more collision. So as I said, whenever you saw the word collision, you should think of momentum conservation. So you write down the momentum conservation equation. So that's the initial momentum of the system because velocity m2 is 0. Now you have, after the collision, m1 and m2 stuck together. So you have this momentum system after the collision. So you can solve for the initial velocity of the bullet v01 from Vf. Now, however, how are we going to solve Vf? We need to use conservation of mechanical energy. Now, the block with the bullet has an initial Vf here, and it's going to swing up. So we have to think what kind of quantity is conserved in this program. So when swinging up, there are two forces acting on the system. You have weight and then you have tension. But tension doesn't do any work because tension is always perpendicular to the direction of displacement. So only gravity is doing work. If only gravity is doing work, mechanical energy is conserved. So we use the equation of mechanical energy conservation. So we find the relation between this height hf and velocity vf, and if you plug in all the numbers, you should find your vf equals 3.57 meter per second. Now we find the vf, we can solve for v01 now from this equation. If you plug in the numbers from the problem, is 896 meter per second. Now, one more example. A two-body collision problem. You have m1, which is 8 kilogram. You have m2. So initially m1 moves 4 meter per second. m2 moves 3 meter per second. m1 is 8 kilogram, m2 is 2 kilogram. After the collision, we know m1 is moving 2 meter per second. This is before, this is after. Now we don't know velocity of m2 after the collision, but we do know it's a collision. So collision momentum is conserved. So we just build a momentum conservation equation, m1 v01 plus m2 v02 equals m1 v f1 plus m2 f2. Now we know everything in this equation except this one, so you plug in all the numbers. 8 times 4 plus 2 times negative 3, because it says this object moving 3 meters in the opposite direction. If we choose this one to be positive, to the left is negative. Equals 8 times 2. Subtract 2 times VF2. And you plug in all the numbers, you find the VF2. The final velocity of M2 is 5 meters per second. So we want to know how much energy is lost during the collision. So you need to find out the kinetic energy before the collision, which is 1/2. Let's call it KE0 times M1 V01 square plus 1/2 M2 V02 square. I think if we plug in all the numbers we find is 82 joules kinetic energy after the collision, and 1/2 M1 VF1 square to VF2 square should be 41 joules. So energy loss is KEF subtract KE0 give us negative 41. That's how much energy is decreased during the collision. For 41 joules was decreased.